All right, guys. So this is chapter 9, part 2. So since I'm not on campus, I've kind of threw together a PowerPoint real quick so that we have something to kind of look at together, I guess. So I'll post this on the Moodle page if you haven't already seen it. And everything I talked about in part 1 is covered in slides 1 through 14. So I'm picking up on slide 15. Okay, so we talked about energy, we talked about heat, temperature. Now let's talk about how we're actually going to calculate energy. Remember, we're going to use the word energy. I'm actually referring to internal energy, but oftentimes the internal part is omitted, so it's just energy. But that's what I'm referring to, is the actual internal energy. So, energy is the exchange between the system and the surroundings. We've kind of already talked about that. Specifically through heat and work. Okay, and we've talked about both of those in part 1. I told you that heat and work are how we transfer energy. Okay, so Q is going to be the abbreviation for heat energy or thermal energy, same thing. W is going to be for work energy. Q and W are not state functions, so their values depend on the process. One way you can tell something is not a state function is I don't include a delta in front of it. So I told you in part 1 that energy is a state function, meaning it only depends on its final and its initial state. So we always talk about energy in terms of the change in energy, okay? Because, well, for one, energy, it's hard to measure directly, okay? So that's why we use final and initial. All right, so Q and W, not state functions. There's no delta. We have a way that we can measure those through the process they undergo, okay? So we're going to be exchanging heat and work through our system and our surroundings, okay? And remember, according to the first law of thermodynamics, the delta E of the universe has to always be 0. Therefore, the delta E of my system is always equal in magnitude, opposite in sign of my surroundings. Okay? All right. So, let's go to the next slide. Let me erase. It's been a minute since I've had to do this, so I've almost forgotten how to do it. All right, so one type of problem that we'll come across when we're looking at finding our delta E is a very simple, I tell you something about the work and the heat, you simply plug it into the equation that, wait, I'm not annotating. You would simply plug it into the Q plus W equation, okay? So what you need to know is you need to know the sign convention for QW and delta E, okay? So let's look at heat first, Q. If the system gains thermal energy, it's going to be positive. So it's gaining energy from the surroundings, okay? Positive. If the system loses thermal energy to the surroundings, your Q is negative, okay? It gives off heat to your surroundings. Then we have work. Work done on my system, it will be positive. If work is done by my system, it is negative, okay? And so the surroundings would be doing the work on the system. Work done by the system, it would be working on the surroundings. All right, then delta E, it's positive if energy flows into the system, and we've said that that is endothermic. It's negative if it flows out of the system, and we said that is exothermic. Specifically, it would be referring to our heat energy. Okay, so energy is exchanged through the between the system and the surroundings through heat and work. So let's look at the next page. Next page, next slide. Okay, it's an example problem. It says calculate the overall change in internal energy. I got this from a different book who uses U instead of delta E. So change that to delta E in joules for a system that absorbs 188 joules of heat and does 141 joules of work. Okay, so if it absorbs heat, it's going to be positive. That's a positive Q. If it does work, that's going to be a negative W. Okay, so remember we're using the equation delta E equals Q plus W. All right, so plug in your Q. It's just a positive 188 joules plus your work. In this case, it's negative 141 joules. Okay, add those together, and you should get 80 something. Minus 141. Oh, what did I say? Not right. It's positive 47 joules. That's what I got. Let me pull out my work example problems. Y'all are here to catch my mistakes because I'm sure there are some, or will be some. All right, yep, that's right. Okay, so that's our simplest problem that we'll see in chapter 9. If I were you, I would go ahead and start making a formula sheet for exam 1. This would be my first formula. Okay. All right, let's see. Moving right along. All right, so let's break it down into heat and work. Let's look at heat first. All right, so this slide says heat is the exchange of thermal energy between system and surroundings. If you aren't tired of me saying that yet, you haven't been listening. Heat exchange occurs when the system and surroundings have different temperatures. That is the reason that you are always transferring heat, is because two things come into contact and they're at different temperatures. That's how ice cools down your drink. It's how your refrigerator works, how your heater works. all of that good stuff. So, something else you might get tired of me saying is temperature is the measure of the average kinetic energy. In this, to be more specific, it's the average thermal energy within a sample of matter. So it's how fast things are moving within that sample. So heat always flows from your high temp to your low temp until both objects equal the same temperature. That temperature is said to be thermal equilibrium. And we'll come across problems that ask you to calculate that temperature at thermal equilibrium. So make sure you know what that actually means. Whew. Okay. Out of breath. I don't know if that's COVID or pregnancy. All right, so one way we can measure heat is through something called the heat capacity. Okay, so when a system absorbs heat, its temperature obviously will increase. The increase in temperature, though, is directly proportional to the amount of heat absorbed. So what determines how much heat is absorbed? Well, it's called the proportionality constant, or it is a proportionality constant called the heat capacity. And that's abbreviated with a capital C. And those units for a heat capacity is either joule over degrees Celsius or joule over Kelvin. Okay, so degrees Celsius and Kelvin are both temperature units. Remember, if you have degrees Celsius and you want Kelvin, you just add 273 to your degrees Celsius. If you want degrees Celsius and you have Kelvin, you subtract 273. All right, so to find your heat, you would say the heat capacity. The heat capacity is a constant for a given substance, okay? So it will always be, you can always look it up. So to find the heat, it's C times delta T. So delta T is going to be change in temperature. So anytime you see a delta, it's always final minus initial. Okay. So if I wanted to find my delta T, it'd be my final minus my initial temperature. All right. So you'd multiply those two together because this is in joule per degree C, we'll say. Our temperature we would want in degrees C, so that these two would cancel and our heat would be some number in joules. Okay, so the larger the heat capacity of the object, the smaller the temperature will rise for a given amount of heat. Whew. So the larger the heat capacity, blah, 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 smaller temperature rise. Some material are more resistant to a temperature change, so they'll have a larger heat capacity. If we flip to the next slide, let me clear this out. Factors that, let's see if I can do this. This might be easier. Factors that affect the heat capacity. The heat capacity of an object depends on the amount of matter present. Therefore, it is an extensive property. Depends on the amount present. So it's usually measured by its mass. That's how you determine the amount. So 200 grams of water will require twice as much heat to raise its temperature by 1 degree Celsius than would 100 grams of water, okay? So you double your amount, you're going to need to double the amount of heat. The heat capacity of an object depends on the type of material. So this is a constant based on what material you're referring to. I don't think I need to read that. So let's go to the next slide. Quantifying heat energy. So we're actually not going to use the heat capacity very often. Because I'm about to show you what we're going to use. So the heat capacity, capital C, is the same thing as the mass times the specific heat of a material. So it is more common for us to be given a mass and a specific heat and asked to calculate how much heat is absorbed or released. So we don't use the heat capacity a lot. Instead, we substitute in the mass and the specific heat capacity. The difference is within this little s here. Okay, so the heat capacity, capital C, but with a subscript S. Okay, so let me make sure I've told you everything. Okay, so the quantity of heat absorbed by an object can be determined from the mass, the specific heat capacity, and its temperature change. Okay, so you could add Q to your formula sheet. That would be your second formula from chapter 9. This would be your third. We will use this a lot more than we will use equation 2, okay? So a lot of times, one way I get you to remember this equation is I say Q equals MCAT, okay? So MC delta T, that looks like it spells cat. So Q equals MCAT, where M is mass, CS is your specific heat capacity, delta T is your temperature change, which again is just your final minus your initial temperature. Okay, so if you look on the next slide, you will see the table on the right gives you several substances and their specific heat capacity. So again, you'll always be given that information unless you don't know the substance. Then you will be asked to find the specific heat capacity. Once you find that specific heat capacity, you can actually identify the substance because you can compare it to this chart or a longer chart, whichever. So, let's see, what do we have? It says the specific heat is an intrinsic, is a measure of the intrinsic ability to absorb heat. Intrinsic, that word, it just means that it belongs naturally to that substance. Okay, so is that substance, if it's a metal, they're usually good heat conductors. If they're non-metals, they're not. So again, it's just built in naturally. The specific heat capacity is defined as the amount of heat energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay, again, we abbreviate it with a capital C, a subscript S, and the units are a little different from your heat capacity. This time it's joules over gram time degrees Celsius, or it could be Kelvin again. The reason we have to add in that gram is because we have mass in our equation, and we want all these units to cancel except the joule to give us our heat, because heat is measured in joules. The molar heat capacity, we won't use that very often. It's just based on 1 mole of a substance instead of 1 gram. So let's look at this problem. So example 9.2 says you find a penny minted before 1982, when pennies were made of pure copper, in the snow. How much heat is absorbed by the penny as it warms from the temperature of the snow, which is -8 degrees Celsius, to the temperature of your body, which is 37 degrees Celsius? Assume the penny is pure copper and has a mass of 3.10 grams. All right, so by assuming it is pure copper, we can flip back over to the previous slide, and you'll notice that pure copper has a specific heat capacity of 0.385. Okay, so we're going to need that. So the specific heat is 0.385 joules over gram times degrees C. Okay, we were given the mass and we were given 2 temperatures. So we were given a final and initial temperature. So delta T is my final temperature first. So it says that originally my penny is -8 degrees Celsius. It's going to warm up to 37 degrees Celsius. So 37 degrees C minus, what did I do? Minus, minus, oh my gosh, y'all. Send help. Okay, did I do it that time? Minus -8 degrees Celsius. Okay, it's always final minus initial, and because the initial is negative, I have to also include that negative there, which actually makes that positive. So my delta T is going to be 45 degrees C. Okay, so I have the 3 variables I need to solve my Q equals MCAT equation. Okay, so plug it in. Mass, 310 grams. Specific heat, 0.385 joule over gram times degrees C times delta T, which we found up above to be 45 degrees. So you'll notice that gram cancels, degrees C cancels. The only unit I'll be left with is joule. So let's multiply those three together. What did I do? You should. Why do I keep getting a decimal place off? Oh my God, I suck at this today. So Q, you should get 53.7 joules. That's how much heat has to be absorbed because it's positive. It's being absorbed by the penny to raise it to 37 degrees Celsius. Okay. So I believe this next slide says, determine whether a shiny gold colored rock is actually gold. Okay, so this is an example where you don't know really what specific heat capacity to use. So you're actually going to find it and then figure out what your substance is. So a chemistry student decides to measure its heat capacity. Another thing, this book also refers to heat capacity and specific heat as the same thing because that they only really use specific heat. Sorry for the confusion. So this chemistry student weighs the rock and finds that it has a mass of 4.7 grams. She then finds that upon absorption of 57.2 joules of heat, the temperature of the rock rises from 25 degrees Celsius to 57 degrees Celsius. Find the specific heat capacity of the substance composing the rock and determine whether the value is consistent with the rock being pure gold. All right, so let's pull out some stuff here. We know the mass. We actually know our heat. It's a positive because it was absorbed. That's how I know it was positive. 57.2 joules. We also know some temperatures. So it doesn't like when I hover. So let's go ahead and find delta T. So delta T would be final. So it rises from 25 to 57. So 57 is final. 25 is initial. So 57 minus 25, 32 is my delta T. All right, so this time I'm given everything except my specific heat. So if my formula is Q equals MCAT, and I want to find specific heat, I'm going to divide both sides by M delta T. It's going to be Q over Q over mass times delta heat will give us our specific heat capacity. That should make sense to you because your specific heat is always in terms of joule gram times degree C. Okay, so plug in your numbers. We got 57.2 joules. Mass is 4.7 grams. delta T is 32 degrees C. That's going to give us our specific heat. Oh, 72, 57.2, sorry, divided by 4.7 times 32. Okay, what I got and what my worked out example says is not the same. Well, just now I got 0.380 joules over gram times delta times degrees Celsius, sorry. That's not what I have on my paper, so I don't know if I did something wrong. Here. I don't know. That's what I got. I hope you got the same and not what I got over here. Okay. I'm going to well, there's actually a another example on this slide, but I don't think I have room to work it out. So I suggest you try it, and then I'll either go over it or I'll give you the answer when we get back to class. So you try to do for more practice here, you're looking for the final temperature this time. So you're still using your Q equals MCAT equation. This time you're just going to try to find your TF, okay? So you guys try that. Wish just told me how long I've been talking. Probably not long enough. All right, so what we're going to do is we're going to stop part 2 here. So do for more practice 9.2, see if you can find the final temperature. I will catch you for chapter 9, part 3.